Good morning. We have a lot to cover today as I'm trying to finish Module 14 for you. Once we finish that, I do have the practice final exam already posted on HomeschoolMinder. I can't send it over text this time because I actually typed it up, so I can't take a picture of it. But it is attached on HomeschoolMinder as a PDF. If you have issues with that, please let me know. You also will have the opportunity, if you complete the test and get a good grade on it, to replace your lowest test grade with this practice test grade. Also, let me see how many points. You have the opportunity to make more points on this test. So let me just, I had added it up for you. Let's see. How many points you have possible. Let me add them up real quick. Make higher than 100 is what I'm trying to say. You can make 134 on this test. I'm trying to help you guys out because I know it's been difficult with you know, having to do class online and stuff. So you have 134 possible points. So you all should get a good grade on this. And if you do the practice exam, I promise you, you will ace the final exam because it is nearly identical. I made them both. So trying to help you guys out. If you need help, as always, I am here. Use your book, use your notes, use whatever you need to get that practice test done and get a good grade on it. And that should really help you out towards the end of the year here. So, all right, just let me know if you have questions. I'm gonna start on page 506 now, and we're gonna just hit all the highlights for the rest of Module 14. So first, let's see, yesterday we talked about the rate equation and did some examples of that. Today we're going to start with rate orders. It's just a little terminology, nothing major. Whenever you use the exponents that we use in the rate equation, the x and the y, those are said to be first order. If it's an exponent of 1, first order with respect to whatever the reactant is. If it's a 2, if the exponent's a 2, you would say it's second order with respect to, and then whatever the reactant is. Excuse me. So for example, the top of page 506 has an equation for you. R equals K, concentration of HNO3, concentration of CuOH2 squared. So you would say that this reaction is first order with respect to HNO3, because the exponent is 1, and second order with respect to CuOH2 because the exponent is 2. And in addition, you would say that the rate equation has an overall order of 3 because the sum of the exponents is equal to 3. So if you add up the exponents, that's going to give you your overall order. I don't think we need too much more practice with that, so I'm just going to go ahead and go on with it. Also, one thing you may have noticed is that in a chemical equation, the exponents sometimes match the stoichiometric coefficients, but that's not always true. So at the top of 507, they wanted to point out that the reaction rate orders for a chemical reaction have to be determined by experiment, like we talked about yesterday. They're not equal to the stoichiometric coefficients in the chemical equation, even though sometimes they might be the same. They are not equal, and you can't just assume that. Sorry, I'm just trying to make sure no one's trying to get in the meeting. Okay, so using rate equations, I'm again on page 507. And let's see, let's look down about 3/4 of the way where it says R equals 0.012 times 0.5, all that equation right there. So this is an example. Suppose we want to run this reaction and we calculate that the rate is 0.0015 molarity per second. What does that actually tell us? Well, according to the definition of reaction rate, this number tells us that every second, the concentration of the reactants will decrease by 0.0015 molarity. But if the reaction concentration is decreasing, what's happening to the rate? Well, like we talked about day 1 on Monday of Module 14, a lower concentration is going to be a lower reaction rate. So as the concentration is decreasing, so is your reaction rate. So this means that the concentration of the reactants will only be that concentration at that point. So if we were to say, let's see, it goes down 0.0015 molarity. So then you recalculate it for the new molarity, and that means you're going to have a lower rate. As you can see in the second equation there, it's 0.00019 molarities per second. And actually, it looks like it went down almost a factor of 10 lower than the initial rate of the chemical reaction. So the rate decreased greatly after that first initial reaction. So as soon as the reaction begins, the concentration of the reactants is going to start decreasing, because think about it, your reactants are getting used up in the beginning of the chemical reaction. Let's see. The rate that we calculate from the rate equation is not the reaction rate throughout the entire reaction. It's just for that concentration. So once the concentration changes, the rate is also going to change. So I'm flipping over to page 508. The concentrations keep going down, so that means your rate is going to keep going down, because as your reactants get used up, then that means they're a smaller concentration of them. That means your rate is slowing down. So that's why we call the rate equation an instantaneous rate, because that's telling us at that instant that the reactants have that concentration that we used. That's what the rate's going to be. And the next instant, when the concentration is lower, that's going to reduce the rate from what we just calculated. So if you look at the figure 14.1 on page 508, you'll see this is how the rate of a reaction changes over time. So as you see, the reaction rate starts quite high. It's about 0.0015. This is the reaction we just looked at on the previous page. So it's starting pretty high, and it decreases very, very quickly and then kind of levels off. So as the reaction rate lowers right away, because as soon as the reaction starts, the concentration of the reactants is lowering, reducing the rate. And a fact that you should know is that when a chemical reaction begins, its rate is the largest that it will ever be, because as the reaction begins, the concentrations are only going down, so the rate is only going to decrease. So when the reaction begins, that is the highest the rate is going to be for the whole reaction. And in the first few minutes of the reaction is when the rate slows down enormously. That's why you see that huge dive in the graph. Then it kind of drops off and just slowly levels out. So a huge drop at first, and then just kind of levels out after that with reaction rate. Look at the next graph on 509. It's figure 14.2. And it's going to show us, the previous graph we looked at was reaction rate over time. And this graph is showing us concentration over time. So notice that at first, the concentration of the reactant again drops very quickly. And this means that the reaction is going very fast. The rate is higher. But the important thing to notice is that it looks like our concentration actually never reaches zero. And this is true because actually the concentration of reactants never reaches zero. And you'll see in blue there, it says chemical reactions never actually finish. They just keep getting slower and slower until they proceed imperceptibly slowly. This means that for any chemical reaction, no matter how long we wait, there will always be some reactants left. And this kind of goes against what we've been thinking, because with our stoichiometry problems, we just assumed there was a limiting reactant that was going to run out during the course of the reaction. It wasn't completely wrong to assume that, because it comes so close to finishing that there's almost none of the limiting reactant left. But just to keep in mind, when we do those types of problems, it is an approximation, because the reactants are never actually running all the way out. Okay, so let's see. Let's talk about temperature in the rate equation, because we did learn that temperature has an effect on the rate, but in a rate equation, we have no factor that speaks to the temperature of the reaction. Sorry, it's more. So it is there, it's a little hidden. Let's see. The temperature is taken care of by the rate constant, that K, that letter K that we talked about yesterday. That does take temperature into consideration. And the rate constant, though it has it in its name, is not totally constant. It does change with temperature. So look there on page 510, figure 14.3. You'll see this is how the rate constant depends on temperature. So this is your rate constant, your K value on the left. The bottom is showing the temperature. So as you see, it's the same, it's the same, it's the same until it hits a certain temperature, and then it goes up. So from this figure, it's telling us that for temperatures below 14 degrees Celsius, the rate constant is very near zero. But as soon as it hits that 14, it starts going up. And the fact that the rate constant increases with increasing temperature is very important to remember. So look at in blue on page 510. The temperature dependence of reaction rate is determined by the variation of the rate constant with temperature. Since the rate constant increases dramatically with increasing temperature, the reaction rate does as well. There is an equation that you can use to determine the exact effect it has, but it's way beyond this chemistry course. So you just need to know a general rule that will help you out. And it works for the type of reactions we're going to talk about under the conditions that we see. So the rate, you'll see at the very bottom in blue on page 510, the rate of many chemical reactions doubles for every 10 degree Celsius increase in temperature. This is a good general rule of thumb. It's a good estimate for standard conditions. So this is just kind of a general rule that we can follow. So example 14.5 is going to kind of go through that. So it tells us a chemist performs the following reaction at a temperature of 25 degrees Celsius. There's your equation. In an earlier example, we determined that its rate equation is as follows, and there's the rate equation. The rate constant for a temperature of 25 degrees Celsius is 0.15, 1 over molarity squared times seconds. What will the instantaneous rate of the reaction be at 25 degrees Celsius if the chemist runs the reaction with both reactants at a concentration of 0.15 molarity? What will be the rate if he runs the reaction at 45 degrees Celsius instead of 25 degrees Celsius? So first, they're asking us two questions. So the first question they're asking us is what is going to be the rate if we change the concentration. So we're going to change, we're just going to plug the numbers into the equation they already gave us, because they gave us the rate constant, the K value, at 25 degrees Celsius, and they gave us the concentrations. So we're just plugging them directly into that equation, and you get the answer. Very easy. But with the temperature change, we can't just use this rate equation, because we just learned that for every 10 degrees Celsius increase, you have a double in your rate, in your reaction rate. So what we're going to do is, let's see, get your reaction rate that you just calculated for those new concentrations, and you're going to multiply it. So the temperature went from 25 to 45, and the rule is telling us that for every 10 degrees is when it doubles. So it went up 10 degrees to 35, and then it went up another 10 degrees to 45. So you multiply that value times 2 times 2, because you have to double it twice, because it went up 20 degrees. So for every 10 degrees, you're doubling. So that 0.00051 molarity per second, multiply that by 2, multiply that by 2 again, because you're doubling it twice since it's going up 20 degrees. And that will give you the reaction rate at 45 degrees Celsius. And as you see, it's a larger number. So it makes sense. It should be, the reaction should be moving more quickly as the temperature is increased. And alternatively, you can, if the temperature is lowered, so say they said we wanted to try the reaction at 15 degrees Celsius, if the reaction, if the temperature is lowered, you're just going to divide the old rate by 2. So instead of multiplying by 2, divide by 2. All right, next page. I think I skipped 2 pages. All right, page 512. Oh, there's Garrett. Hey, Garrett.
Hey.
All right. I am just breezing through the rest of module 14 and just hitting the highlights. So right now I'm on page 512. And I will talk about the final at the end of class again, since you missed it at the beginning. Okay, so page 512, I've been talking about the effect of temperature on the reaction rate in chemical reactions, and we're going to do on your own 14.7. All right, so it says a chemist runs a chemical reaction at 100 degrees Celsius and determines the instantaneous rate to be 0.24 molarity per second. She decides to speed up the reaction by running it at 180 degrees Celsius. What is the new reaction rate? So it looks like we are going to start with the reaction rate we're given, which is let's do 0.24, and that was molarity per second. And the temperature went from 100 degrees to 180 degrees. So for every 10 degrees Celsius, we're doubling. So that means 8 times, right? Because we're going 100 to 110, 110 to 120, 120 to 130, and so on, all the way to 180. So we have 8 times that this value is being doubled. So I'm going to go times 2, times 2, times 2, times 2, times 2, times 2, until you get all the way up to 8 times. So this was 100, 110, 120, 130, 140, 150, 160, 170, 180. And then that will give you, sorry, I did not write the answer down. That's going to give you 61 molarity per second. And as you can see, it is moving much more quickly at 180 degrees Celsius than it was at 100 degrees, as it should, because with a rise in temperature, you're going to have a rise in your reaction rate. So, all right, that is 14.7. Let's do 14.8. And on your own question 14.5, you determined that the reaction rate for the following reaction is, and then it gives you your reaction rate equation. And it's asking us 2 things. Letter A, if a chemist runs this reaction at 30 degrees Celsius with reactant concentrations of 2 molarity each, and then runs the reaction again at 0 degrees Celsius with the same reactant concentrations, what will the reaction rates be in both cases? The reaction constant for this reaction at 30 degrees Celsius is 1.25, 1 over molarity to the 4th power times seconds. All right, so let's work on that one. So first what we're going to do is we're going to solve for it at the 30 degrees. Okay, so we have the reaction rate they give me as R equals K concentration of PO squared, this should be squared, not just a 2, times the concentration of BR subscript, sorry, I can't do subscripts or exponents in here, and that 3 should also be an exponent, so that's to the 3rd power. Now I'm just going to plug in, okay, so they're telling me they want R, so I'm solving for that. They told me the rate constant, which is K, at 30 degrees Celsius is 1.25, 1 over molarity to the 4th power times seconds. All right, and the concentration they told me for both of the reactants is 2.0 molarity. This one's going to be squared, and this one's going to be to the 3rd power. All right. Sorry, the way I type it, it does look confusing. All right. So you have 1.25 times, this is just the unit, times 2 squared times 2 cubed. Okay, just to simplify it. I know there's a lot of units and stuff going on in there, so it's kind of confusing. So your answer will end up being, let's see, 40. I believe. Let me double check. $1.25 times 2 squared times 2 to the 3rd. Yep, 40. So you get 40, and this is your reaction rate, and that's going to be, let's see what our unit's going to be. We have m squared on top, So 2 of these m's are going to disappear from the denominator. So that means I have m squared times seconds on the bottom now. And then I also have 3 m's here on the top, m cubed. So that means 3 of those are also going to cancel, which means I have one remaining on the top. So my final unit is molarity per second, because 5 on the top, 4 on the bottom, so we're left with 1 on the top. I didn't mean to make that more confusing. All right, next, let's see what they asked us in the second part. They said, what will the reaction rate be in both cases? So they also want to know the reaction rate at 0 degrees Celsius. So we just found it at 30, and if we're going to decrease to 0, that means we're going down 3 times, 10 degrees Celsius. So we need to divide by 2 3 times. So that means I'm going to take 40, which was my rate at 30 degrees Celsius, and I'm going to go divided by 2, divided by 2, divided by 2. Okay, so in your calculator, 40 divided by 2, divided by 2, divided by 2. And you should get 5. And the unit is still going to be the same. I haven't changed my unit, molarity per second. Okay, let's see what letter B asked us. Why do the units and the rate constant include m to the 4th power in the denominator? Well, I'm just going to read you what the book says, because they probably say it much better than me. The rate constant needs to be ensured that the calculated reaction rate has units in molarity per second. Since the rate reaction equation yields a concentration in units of molarity to the 5th power, like I said, because we have molarity squared times molarity to the 3rd power, the rate constant needs to cancel out m to the 4th power, leaving m in the numerator, the calculated reaction rate. So in order to get this molarity per second unit that we want for reaction rate, we have to have m to the 4th power in the denominator. So that's all that's saying. Nothing major. All right, so go back to page 512. We are going to quickly talk about catalyst. And I think that's all we have left. And then after that, we'll briefly talk about your final exam, and y'all will be done for the day. All right, so catalyst. We've talked about 3 things that can affect reaction rate. We talked about temperature, so the higher the temperature, the higher your rate of reaction in a chemical reaction. If you increase the concentration of your reactants, that's going to make your reaction rate go more quickly. And if you increase the surface area, so like we took that tablet of antacid and crushed it up and it made it have a greater surface area, that's going to make the reaction run more quickly as well. There's one more thing you can do to make a reaction go more quickly. You can add a catalyst. A catalyst, they give you an experiment that you can do, but we're just going to kind of talk about what a catalyst is and just skip that part since we're kind of in a hurry at the end of the year here. So page 513. What's interesting about catalysts is that they speed up the reaction rate without actually getting used up in the chemical reaction. So go ahead and flip over to page 514. And it's going to tell you here that the catalyst is going to decrease the activation energy. Now, if you remember the beginning of Module 14, we talked about activation energy, and that is the energy that it takes to get the reaction started. And when we looked at those energy diagrams, they would go up a little bit and then they'd go down or whatever, but it would always start with one hump at the top because that's what it takes to get the reaction started. So like lighting a match and putting it on the fire, that's your energy that you have to give it to get it to start reacting. So basically, if your activation energy is lower, then your chemical reaction is going to run faster. And this picture on page 514, figure 14.4, is just showing you how that happens. So in the yellow that you see that's folded there with the hump, you'll see the white, that's your reactants. They have to climb that huge hump to get over. So once they get over, it's taken them longer to get down the hump because it was a larger climb. If you see with a catalyst, it makes that hump smaller. So you don't need as much energy, so you can go ahead and go on more quickly with your reaction. So it makes sense. So what you need to know is that catalysts speed up reaction rates by lowering the activation energy of the reaction. How does it do that? There are 2 ways. And if you'll see on page 515, it gives you those. You have heterogeneous catalysts and you have homogeneous catalysts. And you've heard those words before earlier in the chapter. Just remember, hetero means different and homo means same. So heterogeneous catalysts are catalysts that are in a different phase than the reactants. So say you have reactants in the gas phase, maybe your catalyst is a solid or a liquid. If you have homogeneous catalysts, these are in the same phase as at least one of your reactants. Let's look at some examples of both. They both react very differently in chemical equations. So a first example is a catalytic converter. We talked about that earlier in the year. That is a heterogeneous catalyst. This is the equation that they're showing you where your car has to convert carbon monoxide into carbon dioxide, and you'll see that there. A catalytic converter, because the process is really slow, that equation that you see there, it occurs really slowly. It needs something to speed it up. So that's what the catalytic converter is for. And what it does is it attracts carbon monoxide molecules and oxygen molecules to its surface. So you have your catalytic converter, it's pulling all those molecules up to the top of it. And as they get close to the surface, that means they're getting close to each other, which means they're going to be able to start exchanging electrons and reacting. Because like we've talked about before, it's all about collisions. So the closer you can get the molecules together, the more they're going to collide and react together. So the catalytic converter is drawing them all up to its surface so that they can get together and start reacting. Look at the figure 14.5 at the bottom of page 515. That's just showing you how a heterogeneous catalyst works, and it's by attracting the molecules to its surface, bringing them more closer together than they normally would be, and then once they're close enough, they start exchanging electrons and starting the reaction. That's just a visual for you. All right, page 516. So in the end, this reduces the amount of energy that the molecules need to exert to get close enough to each other. So that energy they would have wasted trying to get close enough to each other is not going to be wasted. They're going to be able to start reacting very quickly. Homogeneous catalysts work totally different. Instead of forcing the molecules closer together, the homogeneous catalyst actually participates in the chemical reaction. It changes the way that the chemicals interact. So you'll see an example here at the top of 516. That is the oxidation of sulfur dioxide, and it is a spontaneous reaction, but it's pretty slow. So nitrogen monoxide gas is known to speed up this reaction without being used up in the reaction. So it's a catalyst. The nitrogen monoxide gas is a catalyst for this reaction, since it's in the same phase as its reactants. So they're all gases. The nitrogen monoxide gas is also a gas. So that would be homogeneous. And how it works is, you'll see that second equation, the 2NO is what it starts with, plus O2. First, it's going to react with the oxygen to make NO2 gas. Then it's going to react with the SO2, and that's going to react more quickly than SO2 and O2. So the NO2 and the SO2 are going to react much more quickly than just SO2 and O2. So then they're going to react and make the SO3 gas, just like the first equation. You're still going to have that product, that same product. So what happened is the NO gas was in the first step of the process and in the next step, and it was produced again, which means it was never used up. It was always there, never actually getting used up in the chemical reaction. If you don't fully understand that, that's okay. You only need to know the difference between homogeneous and heterogeneous catalysts. So in summary, on page 517, homogeneous catalysts change the steps that the reaction takes because it has to react with some of the reactants to get things going, and then it's produced in the end. So it's going to kind of change your equation. Heterogeneous catalysts, they just force the reactants closer together, attracting them to a surface. So two totally different ways that they work, but they accomplish the same purpose. So we're going to do on your own 14.9, 10, and 11, and then we'll be done for the day. So 14.9 says to catalyze the following reaction, solid platinum is often used. Is the platinum a heterogeneous or a homogeneous catalyst? Well, it tells us the platinum is solid and our other two reactants are gases. So we know that the platinum is going to be a heterogeneous catalyst because it is in a different phase than the reactants. So the answer is heterogeneous. 14.10, two energy diagrams for the same reaction are presented below. Which one represents the reaction with a catalyst? Well, as we talked about, the catalyst is going to reduce your activation energy. So which of those diagrams has a lower activation energy? Well, let's look at diagram A. It starts here and it just barely climbs and then it goes on with the reaction. Well, diagram B, it goes really high at first. That means it required a lot of activation energy. So that means diagram A is the reaction that had a catalyst because it had a much lower activation energy. So the answer is diagram A. And lastly, 14.11, it says identify the catalyst in the following reaction mechanism. So it has step 1, and we have H2O2 plus 2, and that's an iodine ion, and that's going to produce H2O and 2IO. And then in step 2, you have H2O plus IO produces H2O, O2, and 2I. So what we're looking for is something that is a reactant in the first step and that is also produced in the final step, meaning it was never used up. So the answer is going to be the iodine ion because, as you see, it is a reactant in step 1. And then in step 2, it is a product, which means it was never actually used up in your chemical reaction. So your answer is the iodine ion, I believe. Let me double check. Yep, the iodine. All right, that is all we have for module 14. So let me just speak to the exam one more time in case you missed it. Hopefully you're listening. Your practice exam is on HomeschoolMinder in PDF form. If you have issues with that, please let me know. Again,
Okay.
I think I added up at the beginning, but I think it was 134 possible points. What'd you say, Garrett? Did you say something?
I just said okay.
Oh, okay. It's 134 possible points, so you should get a good grade on it. And if you get that high, that's totally fine. I'll put that grade in for you, but you have a huge grace period there. And if you have any questions, just let me know. I also said that if you do this practice exam, it will replace your lowest test grade if you do well. And the other thing is, if you do the practice final exam, we're going to go over it Monday and Tuesday, but you should be fully prepared for the final. I prepared them both and they're nearly identical. So do your practice exam. It's going to help you greatly in your final exam. It does cover modules 1 through 13. And yeah, any questions on that?
No.
Okay. Well, if you need any help on it, just reach out, let me know. That will be due Monday, and we'll go over it Monday and Tuesday. So I will need it to grade before we start class on Monday. That way, so, you know, Sunday night.
Oh. Okay.
Yeah, that way we can go over it because I won't know if you did it or not if we start going over it in class. So turn it in Sunday night, Monday morning before class starts. All right, and that's all I have. So unless you have other questions, I will let you go.
Okay.
Have a good weekend.
You too.
Thanks.